As Orson Welles once said, we are born alone, we live alone, and we die alone. And it is only through our friendships and our love that we can pretend for even a moment that we are not alone. I mention this because we will think of the gas phase and particles in the gas phase. Each particle is alone. And that's fine, because that will help us to understand the gas phase and make it simple to understand. But our idea of each gas phase particle, it is alone in its container, which might as well be its universe. So let's pick up with the kinetic molecular theory of gases. And since we will be only talking about ideal gases in this portion, I will call it ideal gases. And that's, and I'll put parentheses around it because that's a Bill Miller insertion, is the ideal gases part. Gases are composed of particles that are flying around very fast in their containers. That is something we've talked about before. And this part, that they are flying around very fast, explains why gases fill their containers. Explains why gases fill their containers. Next part, and then the goal of the kinetic molecular theory of gases or ideal gases is to explain the behavior of gases. B, the size of a particle is negligible compared to the volume of the gas. And we've mentioned some things about this already, but I'll mention them now, re-mention one of them now. So we said that the particle volume is 0.01% of the volume of the container. That means that 99.99% of the volume of the container is empty space. So the volume of a particle, in fact, the volume of all the particles, is negligible compared to the volume of the container. Next thing we want to say is that for a truly ideal gas, each particle has zero volume, and a particle with zero volume is what's called a point particle. And really what that means is that each particle has the entire volume of the container to travel. Each particle has the entire volume of the container. Container, and I said to travel, and but I also might say to itself. And so when we use V as the volume of the container, what we're really saying is that all the other particles in the container that take up some of that little volume, no matter how small, don't count. So the particle acts like V, the volume of the container, is the volume that that particle can move around in. And so our picture of a gas, from the particle's perspective, is that there's a single particle. Let me draw that. There we go. Is that there's a single particle that is a point particle with no volume, and then that particle can move anywhere in the volume. So one particle can move anywhere. So it has this entire volume to travel, and that's why V, the volume of the container, can describe the properties of these particles. Let's see. And so another word that you might use to describe the particle is the gas particle is isolated. So there are no other particles. And so there's no other particles to take up volume, and so there's no, and there's no other particles to interact with. So no IMF, which are intermolecular forces with any other particles. No IMF with any other particles. And so this will make gas particles easy to understand because there's no interactions with other particles. There's nothing for it to do. We can just think of each one particle. And we'll see this later in the course when we talk about something called the ionization energy. We'll think of the ionization energy of a particle in the gas phase because a gas phase particle is isolated and has no other interactions. So the reason that the gas particles are easiest to understand of solid, liquids, and gases is because they're isolated. And it's true, they're only 10 diameters. They're only 10 diameters from each other, but the intermolecular, and they're moving at hundreds of meters per second, but that's enough space so that they act like there's no attractions, no intermolecular forces between particles, and that this particle doesn't even exist compared to taking up any volume of the container. Now the collision of one particle with another or with the walls of the container is elastic. And by elastic, what we mean is that, well, let's write that, elastic. An elastic collision is a collision in which there is no loss of energy. A collision with no loss of energy. And again, so this can happen for gas particles in this kinetic molecular theory of ideal gases, because when these particles collide, there's no interaction. So it's like two billiard balls colliding. So they come in, they bounce off each other, and there was no attractive, no repulsive force, nothing. So a collision with no loss of energy. And then other things we want to say about this is that we want to remind you that the pressure is created by gas particle collisions with the walls of the container. Is created by gas particle collisions with the walls of the container. And we said earlier that pressure was force over area. And we'll talk more about that coming up. Okay. Now, the average kinetic energy of a particle is proportional to the temperature in Kelvin. Let me put that in equation form like we've done earlier in the lecture, in this lecture outline. Kinetic energy, average is due to the bar, is proportional to temperature in Kelvin. Okay? Now, let's go a step farther with this. And let's talk about physics for a minute. In physics, kinetic energy is equal to 1/2 mv squared, where m is the mass in kilograms, V is the velocity in meters per second. And kinetic energy is in joules. And what we would like to say about this is that we can now come up with an equation. Well, let's do some barring here. If we want average kinetic energy, then what we will see, and we won't prove this, though I'm happy to discuss this too, is that it's actually, that's a bar over the V. It's actually the average velocity, because each particle will have its own mass. That will not be averaged. And in fact, generally, we're going to be talking about pure substances when we talk about the velocity and the kinetic energy of gases. So there will be a mass or a molar mass for a substance and a velocity, and the velocity will be averaged over all of the possible velocities. But now what we can do is we can plug in and say, well, these two are equal, these two are proportional, and now I'm going to move this part up here. 1/2 mv squared with v bar here is, sorry, not equal to, is proportional to temperature. And with these two equations, we're going to make our next statements. And our next statements are going to be, well, let's talk about the top one first. For the top one, average, so regardless of the gas, or let's say for any gas, and again, I'll take that away, that's a mistake. For any gas at the same temperature, it has the same average kinetic energy. Has the same average kinetic energy. And in fact, as we will see, and I'm going to add this here, and the same kinetic energy distribution. We can say more than just the average. We can say it has the same kinetic energy distribution. And I guess that should have been in black because it refers to number 1. And the next thing I want to say, and this refers more to number 2, is that let's talk about here. So now we know at the same temperature, if we have a gas where each particle has more mass, because the temperature and the kinetic energy will essentially be proportional to, if it has more mass, then it has a lower average velocity. So for a gas with more mass, it has lower average velocity. And in fact, a lower velocity distribution. And a lower velocity distribution. As we will see. And so I guess that should be, let's call that 3A. 3 and 3A. So these two things we're going to use on the next few pages. So for any gas at the same temperature, it has the same average kinetic energy and the same kinetic energy distribution. And for gases with more mass, it has a lower average velocity and lower velocity distribution. Okay, so let's talk next about kinetic energy. Gas particles have a distribution of kinetic energy values called the Boltzmann distribution. Like we said on the last slide, that is the same for all particles, all gases at the same temperature. So what we're going to do now is we're going to fill in these axes. The x-axis is going to be kinetic energy. The y-axis is going to be fraction of gas particles with a given kinetic energy. Fraction of gas particles with a given kinetic energy. fraction of gas particles with a given kinetic energy. And what these are going to look like is these will always start at 0. So there will be zero fraction of particles with 0 kinetic energy. Then it will rise up steeply. And then it will do essentially what's called an exponential decay until it comes back and touches the x-axis. Okay? And we will make these with no numbers on them. And the only thing we will say, a couple things. So this is for all gases at some temperature. And let's call this, let's do a couple things. So this one's going to be what's called the Boltzmann distribution for all gases at, and we're going to draw a higher temperature one. So let's call this for all gases at 300 Kelvin. Now, before I draw the next line, let's do a couple points here. I'm actually pointing to the spot where that is the average kinetic energy. The average kinetic energy is always a little past the peak or the highest fraction. And that's because if you average these ones and these ones, some of which are very high, the average is right here. So for all gases at 300 Kelvin, this is the average kinetic energy, K bar. And let me point out one other point on the same plot. So this one right here is the most probable kinetic energy. The most probable kinetic energy because it has the highest fraction. Now, let's move into a second color. And we know that average kinetic energy is proportional to temperature in Kelvin. And that means that if I go from 300 Kelvin, where my average is right here, and then to 600 Kelvin, that's doubling it, then my average kinetic energy should double as well. Let's see how good I am at drawing this. And it goes something like this. So right here, Ke bar for all gases, and it's supposed to be just on the red line. I know it's weird it crosses there, but it's on the red line. Ke bar for all gases at 600 Kelvin. So temperature is doubled, average kinetic energy is doubled. And two other things I'll say. The most probable is again here at the top. And since these two are fractions and that all of the fractions have to add up to 1, the area under each of these curves is exactly the same. It's like we've squished the first curve to higher kinetic energies. Okay. Now, typical questions might be draw a Boltzmann distribution of kinetic energy values at 300 and 600 Kelvin for nitrogen. Another question would be draw the kinetic energy distribution for nitrogen at 300 Kelvin and oxygen at 300 Kelvin. And you would say to me, or you would draw for me, one curve and you would point to it and you would say, this curve is for both nitrogen and oxygen at 300 Kelvin because it is for all gases. And that's when kinetic energy is on the x-axis. Mass does not matter for kinetic energy. Velocity doesn't matter for kinetic energy. They're the same. Speaking of kinetic energy. However, but at the same temperature, all gases have different masses and will therefore have different velocities or different speeds. And so this here, my x-axis is molecular velocity. My y-axis is relative number of molecules with indicated velocity. And when relative number, another word for the relative number is the fraction. Fraction of molecules with indicated or given velocity. And here we can see, so first off we get an idea of just how fast something like hydrogen is moving. It's moving on average with an average velocity of approximately 2,000 or 2,000 plus meters per second. Helium and then even oxygen has an average velocity of somewhere around 460, 480 meters per second. And then of course as you get heavier, your velocities slow down until eventually your velocity is slow enough that you end up in the liquid phase. And you're not gases anymore. So when velocity is on the x-axis, all of the different gases have different curves with different average velocities. Now here are some other typical questions that you might see on exams. Given two corked flasks with the same volume, same temperature, one has 0.2 moles of oxygen, another has 0.2 moles of argon. So these are two different substances. We might ask the question, which flask has a higher pressure? Well, we see higher average kinetic energy and velocity. Let's deal with pressure first. Whenever we think about pressure, think about the ideal gas law. And we can write it generally, or we could write it specifically for either oxygen or argon. However, if we have the same volume, the same temperature, the same constant R, of course, and the same moles, we can say that the pressure for each of these gases, or the partial pressure for each gas, will be the same. So which flask has a higher pressure? So the one with the oxygen or one with the argon. So the pressures will be the same. Because the moles are the same, so the volume, R, and T, everything else is the same, so the pressures must be the same too. Now let's get back to what we were just talking about. Which flask has particles with higher average kinetic energy? Well, if temperature is the same, average kinetic energy is the same, so average kinetic energy will be the same. For C, which flask has particles with higher average velocity? To do that, we need to know their molar masses. And I've got my periodic table around here somewhere. There it is. So oxygen, O2, is going to be 32 grams per mole. Argon is going to be 40, or just 39.95 grams per mole. So argon is heavier. O2 is lighter, or has less mass, and it will have the higher average velocity. Where I've got V bar for average velocity. So that's for moles, and we'll also ask a question about grams of these two. Same volume, same temperature. As soon as you've got the same temperature, you know that the average kinetic energy is the same. Same for both. So it does not matter which question we're asking here. Same with the flask has particles with higher average velocity. Still the same, oxygen is lighter. Has higher average velocity. But now let's look at the pressure. We go back to our ideal gas law. We decide that T, R, and V are all the same, but what about N? Well, we now have the same grams of each of them. when you have the same grams, you can find the moles. We said oxygen was lighter. That means it's going to have a smaller molar mass. And 0.2 grams divided by the smaller number will be more moles. So O2 has more moles. More moles is going to lead to more pressure. So O2 has more moles, has higher pressure. And that's a way of working this question without using any math. Of course, if you wanted to work this with math, you could make up a volume of 1 liter. You could make up a temperature of 300 Kelvin. You could then actually find the moles of each of these and actually calculate the pressure. There are many ways to get the answer, and sometimes it's through thought process, and sometimes it's through math, and sometimes both can help to do.